Hi guys, Dr. Colbreth here with number 20 from chapter 16. It says the lowest frequency in the audible range is 20 hertz. What are the lengths of A, the shortest open tube, and B, the shortest open closed tube needed to produce this frequency? And this is meaning a standing wave at this frequency. All instruments require a standing wave at the fundamental frequency in order for that to work, or the lowest frequency. So let's take a look at A, which is the open tube to begin with. So the boundary conditions on an open tube in terms of the displacement, meaning how the sound is displaced left to right, is an antinode on each end. But it might be easier to think about the pressure wave to see how those boundary conditions work out. And the pressure wave, wherever we have an antinode, we have a node. So we have an inverse relationship here with a node at each end. And this is our familiar rainbow shape, or for the fundamental frequency, which goes node to node, which is half of a wavelength. And in fact, this is also half of a wavelength. It's a quarter plus a quarter, which is equal to a half. So either way we look at it, for an open tube, we need the length of the tube to be equal to half of the wavelength in order to produce a standing wave and satisfy the boundary conditions on the tube. Now we're not given the wavelength in this case. Instead, we're given the frequency, which is equal to 20 hertz. And this is a device operating on a sound wave, which means that its speed is going to be the speed of sound, 343 meters per second. So now we can use the fundamental relationship for sinusoidal waves, that the velocity is meters per second, meaning lambda times f. V is equal to lambda times f, or lambda is equal to v over f. We can plug that into our expression here for the length of the tube. We get that L is equal to v over f divided by 2, or L is equal to v divided by 2 times f, which is equal to 343 meters per second divided by 2 times 20 hertz, which is equal to 8.6 meters. More than 25 feet. So we need a large tube to accommodate a low sound like this, and so this would be something similar to a didgeridoo. But if you want the lowest audible frequency to work in your didgeridoo, you're going to need a very long didgeridoo to make that happen, which is an example of an open tube. Or I guess your mouth is on it. It could be an open-closed tube. But we're going to do an open-closed tube next. Let's go ahead and do that now. For an open-closed tube, the boundary conditions are different. For an open-closed tube, we need to have a node on this end and an antinode on the other end. So the largest wave that satisfies that boundary condition is going to be this one here. And this is 1/4 of a wavelength. Going from node to antinode is 1/4 of the full sine wave here. So we get that the length of the tube is equal to lambda over 4. And nothing about our wave has changed. It's still at 20 hertz. It's still at 343 meters per second. So we can plug the same expression in here, that lambda is equal to v over f for the length of the tube in this case. And so we're going to get that L is equal to 343 meters per second divided by 4 times 20 hertz. And this is just twice as big as, or 1/2 is the size that it was before, a tube length of 4.3 meters.